What if everything you thought you knew about the Big Bang was wrong? For decades, we've been taught that our universe began in a single explosive moment, a colossal burst of energy from an infinitely dense point. That moment has shaped not just scientific models, but our entire understanding of where everything comes from. Yet new discoveries emerging from the frontier of quantum gravity are challenging that story in ways that feel almost unbelievable. Tonight, prepare to stretch your imagination as far as it can go. Because the deeper scientists look, the more it seems that the Big Bang may not have been the beginning at all. Imagine the universe as a stage. For years, the opening act has always been the same, a singularity, a point where the laws of physics collapse under the weight of infinite density and infinite temperature. It's the boundary line where time itself was assumed to begin. But here's the mystery that refuses to be ignored. A singularity isn't just strange. It's a mathematical red flag. It's physics throwing up its hands and saying, I don't know what comes before this. And that is a major problem, because we don't want a theory that stops at the most important moment in the universe's history. We want an explanation that works all the way down to the foundations. The Big Bang Theory has earned its place in science by explaining what happened after the earliest measurable fraction of a second. It beautifully accounts for the expanding universe, the abundance of light elements, and the cosmic microwave background. It's one of the most successful models we've ever created. Yet even with all its triumphs, it sidesteps the deepest question of all. What actually triggered the birth of the universe? Why did the cosmos suddenly emerge? What existed before Titazo? Or does that question even make sense? This is where quantum gravity enters the story. Not as an abstract mathematical puzzle, but as a genuine attempt to uncover cosmic truth. At the heart of this scientific revolution is a clash so fundamental that it has shaped the last century of physics. On one side stands general relativity, Einstein's masterpiece, which describes the curvature of space and time on the largest scales, galaxies, black holes, and the universe as a whole. On the other side stands quantum mechanics, the rulebook that governs particles, forces, and the smallest building blocks of reality. Both theories work with astonishing precision in their respective domains. But when you try to make them operate together, especially in extreme conditions like the early universe, they tear each other apart. It's as if the universe speaks two different languages, and quantum gravity is humanity's attempt to translate between them. One approach to this translation is string theory, a bold attempt to replace point-like particles with tiny vibrating strings. According to this idea, everything in the universe, matter, energy, even space itself, emerges from these minuscule filaments dancing in multidimensional space. Another contender is loop quantum gravity, which imagines that spacetime is woven from discrete loops forming a vast quantum network. Both theories may seem exotic, even alien, but what unites them is the idea that the universe is not smooth at its smallest scales. Instead, it seethes and ripples like a stormy ocean. Physicists call this landscape quantum foam. At unimaginably tiny distances, spacetime is believed to churn with fluctuations, constantly creating and destroying virtual particles, bubbles, and distortions. It's chaotic, wild, and nothing like the calm, predictable geometry we experience. But it's also the key to understanding how the universe behaved before it grew large enough to follow the familiar rules of gravity and geometry. If we can understand the structure of this quantum foam, we can begin to imagine a cosmos that didn't emerge from an impossible singularity, but from a more natural quantum origin. And that leads to one of the most revolutionary ideas in modern cosmology. Maybe the Big Bang wasn't the beginning. Maybe it was a transition. In several versions of loop quantum gravity, the universe doesn't begin with a singularity. Instead, it undergoes a bounce. In this scenario, a previous universe reached a point of maximum compression, then rebounded and expanded into the universe we inhabit today. The Big Bang becomes less like a creation event and more like a cosmic heartbeat, an oscillation in an endless cycle of contractions and expansions. In this view, every universe that bounces leaves behind clues that the next universe might one day decode. There's another possibility just as astonishing: eternal inflation. In this idea, our universe is just one bubble inside a vast cosmic sea, with new universes constantly budding and growing. Some physicists propose that quantum gravity makes it possible for baby universes to form from fluctuations in the quantum foam itself. Each bubble could have its own laws of physics, its own dimensions, its own story. If this is true, the Big Bang wasn't the beginning of everything. It was simply the beginning of our own local region within an infinitely larger, ever-evolving multiverse. These ideas push the limits of imagination, but they all share the same goal: explaining what came before the moment we call the Big Bang. They offer a universe where time didn't simply start from nothing, but where the flow of time extends beyond the horizon of our cosmic memory. A universe where the question, what happened before the beginning, is not only meaningful but necessary. But here's where the mystery deepens even further. How do you test something that happened before the observable universe? How do you gather evidence for events that occurred beyond the reach of telescopes and detectors? The challenge is staggering, but physicists are developing ingenious ways to look for signs that quantum gravity left behind fingerprints in the earliest cosmic light. One of the most promising methods involves searching for primordial gravitational waves, subtle ripples in space-time created during the universe's infancy. These waves could carry information older than the light in the cosmic microwave background. If scientists can measure their properties with enough precision, they might find deviations that point toward a bounce or toward quantum structures imprinted on the fabric of the universe. These would be whispers from before the cosmic dawn. Another possibility lies in patterns within the cosmic microwave background itself, the afterglow of the early universe. Some models predict faint anomalies, tiny twists or fluctuations, that could reveal how quantum gravity shaped the universe's earliest moments. Though incredibly difficult to detect, future observatories and satellite missions may soon have the sensitivity to uncover these signatures. If they do, humanity will catch its first empirical glimpse of a universe older than the Big Bang. As we move deeper into this frontier, the conversation becomes more than just scientific. If the Big Bang wasn't the true beginning, then our origin story becomes far richer, far stranger, and far more beautiful than we ever imagined. It reshapes how we see ourselves, not as beings looking back at a single moment of creation, but as participants in a cosmic process that stretches far beyond our familiar timeline. It blurs the boundary between physics and philosophy, pushing us to confront questions that touch the core of meaning itself. What does it mean to exist in a universe that may never have started? What does it mean if reality is part of a larger multiverse? How do we redefine our place in a cosmos that may be infinite, not just in space, but in time? Quantum gravity forces us to rethink everything, from the nature of time to the fabric of existence. It paints a picture of a universe far more intricate and alive than the simple models of the past. And while much of its story remains unfinished, its potential is breathtaking. Over the coming decades, advances in particle physics, gravitational wave astronomy, and quantum technology may finally reveal the full tapestry of the cosmos, showing us not only how our universe was born, but whether it truly had a beginning at all. The journey to answer these questions is just beginning, and it promises to be one of humanity's greatest intellectual adventures. If quantum gravity succeeds in rewriting the story of cosmic origins, it won't just change science. It will change how we understand reality itself.